Hi, my name's Stephen Nowell. I'm the Director of Technical Support here at Stardog. I've been with the company since way back in 2012, doing engineering work on all of the various engineering teams. So I've now shifted into more of a support and training-oriented role, but I still do as much engineering as I can get away with. In today's Getting Started with Data Modeling webinar, I plan to start out with just a brief overview of RDF and Graph for those who might not be as familiar with it. And then I'll move into the standard domain modeling languages of RDFS and OWL. After that, I'll be going over some of the guidelines and the best practices for both domain modeling and ontology development. So here's an example of an RDF graph. It's just a small snippet from a larger music data set that we have. In a graph, you have nodes that represent the entities and then edges that represent the relationships between them. In this graph, you can see we have a node representing the band The Beatles, nodes that represent each of its members, one of their studio albums, and then a song from that album. Each of the nodes has an identifier which shows the entity that it represents, and then each edge has an identifier that tells us what kind of relationship exists between those two nodes. For example, the member edge links the band to its members. Edges are directional, so the member edge goes from the band to the member. You'll notice that all of the edges start at a node that represents a specific entity, and then connects that node to either another entity or a piece of data, like a string, a date, or a number. There's also a special built-in edge identifier called RDF type that you'll see on there that links entities to special nodes that represent their classes. So in this case, the Beatles node has the type band, and John Lennon has the type solo artist, and so on. In this graph, we also have nodes depicted in green that represent data type values, such as strings, numbers, or dates. For example, we can see that the length of the song Love Me Do is 125 seconds. The release date of the album Please Please Me is March 22nd, 1963, and so on. RDF has special terminology to refer to the nodes and the edges in a graph. An edge is referred to as a triple because each edge has three components. The source node is called the subject, and the target node is called the object. The edge identifier that specifies the relationship between them is called the predicate. The identifiers used for predicates are called properties. So in this case, member is a property that is used in the predicate position of the triple that we see here. And much like a regular sentence, you can read a triple as subject, predicate, object. Or in this case, the Beatles has member John Lennon. Formally, an RDF graph is just defined as a set of triples. Triples are serialized by simply writing the subject, predicate, and object, followed by a period. Typing out the full IRIs every single time you use them would get incredibly tedious. So fortunately, you can define prefixes to shorten IRIs. Defining a prefix lets you just specify the beginning part of it or the namespace, so that you then only need the end or the local name. So in this case, I define the RDF prefix so that in the data, I can just type RDF:type instead of the long, nasty string. I've also defined a prefix with an empty string. We call this the default namespace. So for example, the entity, the IRI for the Beatles, is represented by the URI http://stardog.com/tutorial/thebeatles. However, since I have the prefix defined, I can simply, in my data, write :the Beatles. It makes things a lot easier. The next few slides here are just to point out some of the shorthand for RDF that you'll be seeing throughout the rest of the presentation. Here we have a graph that contains 5 triples. All 5 of them are explicitly spelled out. What's called the turtle syntax allows you to drop data types when they can be inferred. In this case, 125 has no decimal point in it, so it can only be an integer, so we don't need to explicitly say that. RDF type is an incredibly common predicate that allows us to state that an entity belongs to an RDF class, or in this case, Love Me Do is a song, so we can shorten this to just A. Now you might notice that the subject of all 5 of these triples is Love Me Do. We don't have to repeat it all 5 times. By ending lines 1 through 4 with a semicolon instead of a period, we can ignore the subject of the next triple because it's the same. So this, along with some indentation purely for aesthetics, makes things a little bit more readable. However, you might also notice that not only is the subject shared between all 5 of these triples, but those last 2 even have the same predicate of writer. So we can shorten that down further by putting a comma between John Lennon and Paul McCartney. As I did too earlier, space and indentation here doesn't matter, so we can format the block any way we feel like, and you can see this is a lot nicer looking and a little bit easier to read than having to parse through all 5 of them, subject, predicate, object, every single time. So you'll be seeing this a lot for the rest of the presentation. Now that we've seen how to describe the data itself with RDF, however, RDF doesn't provide us with any kind of vocabulary to define our schema or the structure of the data. So for this, we have RDF schema, or RDFS, for the basics, and then web ontology language, or OWL, to even better define the relationships between our data elements. As I mentioned earlier, RDFS introduces the concept of a class. So a class here is simply a category of nodes with similar characteristics. In this case, I'm declaring band to be a class by using RDF type as the predicate. Then I'm declaring the Beatles to be a band using that A shortcut. Classes are organized into a hierarchy via the RDFS subclass of predicate. So for example, if I define vehicle as a class, I can then specify car, truck, and boat as subclasses of it. This is incredibly beneficial because I can declare something in my data to be of type car, and because this definition exists, it will also be inferred to have type vehicle without me having to explicitly say that. Properties are the relationships or the predicates that connect the instances of our classes. One unique feature of the RDF data model is that a class is not defined in terms of the properties its instance may have. Rather, properties are defined in the terms of the kinds of subjects and objects they relate. This is done via domain and range definitions. RDFS domain indicates the class to which all subjects must belong when using the predicate, and likewise, RDFS range indicates the class or the data type of those triples objects. So here we see that any triple using the hasTrack property will be of the form album, hasTrack, song. And we'll also have triples with the pattern some song, length, some integer. Properties can also be hierarchical. It's perhaps a little less common than using subclasses, but you could say, for example, that mother of is a subproperty of parent of, and the inference will work the same way as for a subclass. So RDFS also provides these label and comment predicates to let you define both a human-readable name and a human-readable description for your classes and properties. Their use is heavily encouraged to help flesh out your ontology and make it more user-friendly to anyone reading through it. There are also standard values to use in things like form labels or tooltips in an application that uses the ontology. We'll move on now to the web ontology language, or OWL. It is an expressive ontology language that builds on top of RDFS and contains formal semantics based on description logics. OWL also defines class and property, but it goes into just a little bit more detail than RDFS does. So here we're defining the same 2 properties as before, but we're using OWL's object property and data type property classes. Declaring a property to be an object property means that it will be connecting entities to other entities, whereas a data type property connects an entity to a piece of data, or a literal, as RDF calls it, which is a string, an integer, a date, etc. A few examples of some property characteristics that can be defined using OWL. Say we have this writer property here. It obviously has a direction associated with it. In this case, Queenie I has a writer of Paul McCartney. OWL lets us define another property as an inverse to writer. In this case, we'll call it writer of. By using a reasoner, it will allow us to take the existing relationship that we see here and infer a relationship going in the other direction without, again, having to be explicit about it. We have transitive properties, which allow us to infer a new edge between two nodes that are connected via a path of the same property. So if I define co-writer here as a subproperty of connected to, then the explicit co-writer relations will also be classified as connected to. If I then define that connected to as a transitive property, we can say that because A goes to B and B goes to C, it implies A goes to C, and we can infer this additional connected to relationship. Property can also be defined as a symmetric property, and that means that the direction is irrelevant, and in fact the relationship is bidirectional. So in this case, if connected to is symmetric and Paul McCartney is connected to Adele, then we also know that Adele is connected to Paul McCartney. OWL provides us with a number of definitions like this. However, for the sake of brevity, I'll be moving on to the modeling and the ontology development portion. It's important to note here, before we start, that there is no single right way to model a domain. A data scientist might see things one way, while a domain subject matter expert sees them another. Neither would create the wrong model, although it's important to make sure that the end result is something that's both usable and agreed upon by everybody involved. Your model should be built iteratively, starting with a minimal version and building on it, and normal engineering guidelines and best practices should be used as you create your model. 4 things I want us to consider when talking about ontology development are that you should determine the scope of the ontology, enumerate important entities, build the class hierarchy, and specify the relationship between entities. So we'll start with the scope of the ontology. You want to make as small of an ontological commitment as possible. It is very easy to get carried away right at the beginning and start modeling everything in your domain or everything in your field of expertise. This is a really good way to overcommit and never actually finish developing or producing any useful artifacts. It's a good idea to stay general while making sure that your ontology is specific enough to cover all the use cases. You do this by generating competency questions that your ontology must be able to answer. In short, keep the scope limited and general while ensuring that it will accomplish what you're setting out to do in the first place. Next up, we need to determine our core classes, properties, and individuals. This is obviously incredibly domain specific, but let's say we're making a financial services ontology. So some core classes might be financial institutions, split up into banks, credit unions, investment houses. You could have people split into lenders and borrowers and fund managers, etc. Some core properties could link lenders to borrowers or lenders to financial institutions, fund managers to investment houses, and so on. Doing this helps to set the scope and the structure of your ontology. If possible, try to reuse terms, especially the more standardized terms. Examples of this, here are a few widely accepted schemas for various domains. RDFS label and RDFS comment, we already went over. Friend of a friend, or FOF, is a schema that dates back to 2000 for describing people and their relationships and is very widely accepted. Dublin Core is another one used for describing physical and digital media, and there are many others around. The point here is that unless the domain demands it, you should avoid coming up with new terms that mean the same things, like DC title or DC author for documents, or FOF relationships for people. When coming up with the terms for your ontology, there are a few decisions that you need to make with the types of terms that you want to use to represent things. So you have the class versus property decision, as in, you have a red thing. Should you represent that as a thing that has the class red, or as a thing with a has color predicate that has the object value of red? Or class versus individual, where if you have, say, a bank class, should that be a subclass of an organization class? Or should the bank itself be an instance with type organization? There really isn't a right or a wrong answer to these questions, as it is entirely dependent on what makes sense for your use case. The important thing is that you are consistent across the entire ontology. Third up, we need to determine the class hierarchy, which really is the backbone of the ontology. There are some simple guidelines to follow, which we'll cover in just a second, but it's good to emphasize the need to be pragmatic above all else. The slide here says to avoid deep philosophical debates, and that comes from experience that folks at Stardog have from various working groups over the years. In software engineering, we have the term bike shedding for this, which comes from a hypothetical group that's working on plans for a nuclear power plant that spend an absurd amount of time on unimportant things like the materials for the bike shed outside of the plant, instead of focusing on the bigger picture. It's very tempting and very easy to do this, but it is far better to ever actually get the ontology developed. When you're creating your class hierarchy, add classes as needed, but make sure that your subclasses have enough differentiating characteristics from their superclass. In other words, when you're adding a subclass, there should still be at least one instance of the superclass, otherwise, why are you bothering? When you're subclassing, pay attention to the number of subclasses for a given class. If you have just a single subclass that shows either incompleteness or redundancy, as there would be essentially no difference between the subclass and the superclass. On the other side, if you have too many subclasses of the same class, you probably don't have enough categories. Your superclass needs some more siblings. Example of that being if you had 100 different subclasses of animal, you could make mammal and insect and then group things underneath that. You want to be consistent in your modeling. The siblings should be homogeneous, as should your use of subclasses versus like part-whole relations. An example of that is like a family being made up of parents and children. Lastly, we need to specify the relationships between our entities. Remember that properties are defined by the classes that use them and not the other way around. So for each property you have to consider which class can, should, or must be used by it. Keep in mind both object properties that relate entity to entity and data type properties that relate entity to literal or piece of data. As you're defining the domain and range of properties, know that they can be defined both globally and locally. I haven't really touched on it thus far, but OWL does allow you to define local properties that are true for specific classes versus the global RDFS domain and RDFS range. So in this example at the bottom, I could define hasParent to have an RDFS domain and RDFS range of some class human, but what if I then need to model animal families? Well, in this case, I would either need some separate hasParent property for animals, or I would just need to rework it entirely. In this local case, OWL lets me say that hasParent has a range of human, but only for human subjects. So it allows me to get very specific with what my data is going to look like. To close out here, I just want to cover a few practical considerations, including your naming scheme, ontology modularity, ontology version, and testing and debugging. Any naming scheme works well, but it has to be consistent. Examples of differences here include the direction of the relationship itself. Do you want hasEmployer versus hasEmployee? Your capitalization and delimiters. If I have employer, has_employer. Any suffix or prefix conventions. I could have employee of, is employee of, has employer, employs, works for. Any of those are all basically the same idea. And then your singular versus plural nouns and verbs. Again, any of these things works, but being consistent is key. You don't want something in your data like A employee B and then B has employer A. It just breeds confusion. Annotations are great to use too, instead of overloading names. RDFS label and RDFS comment are your friends here, as they help to improve clarity and avoid misuse. Moving on to modularity, a single monolithic ontology is hard to maintain, not to mention it's hard to develop or finish in the first place. What helps is to divide your domain into submodules. So, for example, if we have a financial domain, we could have a submodule for banking, one for loans, one for mutual funds, and so on. Use separate ontologies and namespaces for each of these modules, but then reuse and share as many terms between them as possible. So the banking and loan modules might have the same class to represent people or currencies. You can think of the ontology modules as being in layers. So at the top is all of the general knowledge. These are things like the FOF schema we mentioned earlier for people, or things that apply very broadly. In the middle, you have knowledge that is domain-specific, but still shared between the various models, like the currency example just now. And then at the bottom are the classes and properties that are specific to each individual module. Ontologies should be considered IT artifacts. As such, they should be placed in version control, like Git or SVN. It's also a good idea to semantically version the ontology. The version ID should be structured and meaningful, and the rules behind version number changes should be well understood. I recommend using something like SemVer. Essentially what that is versioning your artifacts in the form x.y.z, where those are all integers, signifying a major version, a minor version, and a patch version. Then you can also put additional labels like snapshot or beta or something at the end as needed. From the semver.org website directly, if you have version XYZ, you increment the major version of X when you make incompatible changes, the minor version Y when you add functionality in a backwards compatible manner, and then the patch version Z when you make a backwards compatible bug fix. So just based on how your version number changes, a user can immediately tell what level of change it was. Especially they can tell if something might break if you go to a new major version. The ontology that you have needs to have an ontology IRI. Optionally, it can have a version IRI as well, as you can see in this example. Here we have example.com/ont is the ontology IRI, and then the 2.0 IRI is for its version. Your ontology/version IRI pair should be unique. But if you have no version IRI, then your ontology IRI itself needs to be unique. To test out your ontology, you need to check it for logical errors. This includes unsatisfiable classes and inconsistent instances. Luckily, Stardog provides tools that can not only check your instance for inconsistency, but it can also explain to you exactly how it's inconsistent. You also want to detect any unintentional inferences. So in the case where you have a derived subclass defined a little too broadly, things might get classified as members of that class that shouldn't be. And finally, you can develop unit tests in any given testing framework consisting of Sparkle queries and expected results. So we can move on to the Q&A portion here. Okay, I do have one question here of what other general schemas are available? What do they represent? So I did have some of these on the slide when we were talking about the FOF schema and the DC terms schema. There are a few other ones. You have SCOS, which is the Simple Knowledge Organization System. That's a common data model for sharing and linking knowledge organization systems themselves. Schema.org is a broad schema for structured data. There's one called Good Relations, which is used for e-commerce. GeoSparkle for geospatial relations. The OBO Foundry was Open Biological and Biomedical Ontology. So chances are for a lot of the really big domains, there might already be a schema that exists that you can sort of work off of. Okay, I also have a question here about a little more detail in the class versus individual terms. So yeah, if you recall on the slide, I mentioned that the class versus individual, if you have a bank, should that be a subclass of the organization class, or should bank itself be an instance with type organization? So it mostly depends on how much farther down you need to go with it. If your ontology is just going to represent all banks as a group, then it might make sense to have just one bank entity that has type organization. However, if you plan to further subclass banks, like into mortgage banks or personal banks, or define entities that themselves are banks, like Chase or JP Morgan or Bank of America, it would make a lot more sense to declare bank as a subclass of organization, and then the further subclasses or instances from there. Actually, I see somebody else is bringing up FIBO here. That's a very large financial ontology being developed by a couple of banks, and I know that Stardog was somewhat involved in that. I know they just came out, I think, somewhat recently with like a version 1.0. Yeah, you can look up FIBO, FIBO, for all sorts of financial institution schema work. I do see a couple other questions on here, but I'm not sure that I can answer them with the proper authority. So I might be able to follow up with you after this. So I do have one that just came in here. Do vocabs like the Dublin core define schema between classes, or just define the classes and properties without defining the relationships between classes? So kind of like we covered, where was I going with that? Yeah, so the properties as defined, you define them by the classes that they use. So in defining the properties, it kind of inherently defines the relationship between classes. So yeah, for each property in Dublin core, really in any schema, you'll have the class definitions and then the property definitions relating all of those classes to each other. I hope that made enough sense. Let's see, when starting with large ontologies like FIBO, would you recommend starting from scratch and building up, or starting from the whole and start deleting? So again, it's very easy to start and just start modeling everything. So I would think in my experience, if you start modeling everything, you're not going to want to start deleting things off of it. So you might just end up with a big mess. So kind of what we recommend is maybe not necessarily starting from scratch. Start with a group of questions that this ontology needs to answer, and then come up with the minimal amount that will satisfy those questions. And then once you have that, then you can build it up from there to answer other questions or to be more specific about things, that kind of good stuff.